Medical imaging is the technique and process of creating visual representations of the interior of a body for clinical analysis and medical intervention, as well as visual representation of the function of some organs or tissues. Medical imaging seeks to reveal internal structures hidden by the skin and bones, as well as to diagnose and treat diseases. Medical imaging also establishes a database of normal anatomy and physiology to make it possible to identify abnormalities. Although imaging of removed organs and tissues can be performed for medical reasons, such procedures are usually considered part of pathology instead of medical imaging. As a discipline, and in its widest sense, it is part of biological imaging and incorporates radiology, which uses the imaging technologies which are known as the biomedical imaging devices. In this video, we will show you 5 of the most common biomedical imaging devices that are used worldwide.
So, elastography. This is a novel imaging modality which depends on the same differences in mechanical properties between a healthy and abnormal tissues, but uses imaging in detecting these depths not reachable by manual palpation. Manual palpation is using one's hand and examining a body to diagnose an illness or disease. Now, there are numerous elastographic techniques, but what they have in common is that they create a distortion in the tissue, observe and process the tissue response, then display the results to the operators, usually through image. So in inducing a distortion, it tests how it behaves when deformed. We have 3 actions that can be applied in inducing a distortion. First, by vibrating the surface of the body or organ with a probe. Second, is using a radiation or focus of ultrasound to push or create a push inside the tissue. And third, is using distortions created by normal physiological processes. Example of these are pulse or heartbeat. Next, after getting the response has been observed, it is the time where the stiffness can be calculated from it. We have 2 principles that can be applied in observing the response. For a given applied force, stiffer tissues deforms less than the softer tissue. And last, mechanical waves travel faster through a stiffer tissue than the softer ones. So in observing a response through image, there are 3 types. It can be a 1-dimensional or a line, it can be a 2-dimensional or a plane, and a 3-dimensional or a volume. One application in elastography is magnetic resonance elastography. So in this process, it uses a mechanical vibrator on the surface of the body, then shear waves will be produced in it. Then the shear waves will travel through the patient's tissues. And then after that, the velocity of the waves is used, and this will be used to infer the stiffness of the tissue. Other applications of elastography is the ultrasound elastography, transshed elastography, or quasi-static elastography.
The next medical technology is the magnetic resonance imaging, or MRI. MRI uses a powerful magnets to polarize and excite hydrogen nuclei of water molecules in human tissue, producing a detectable signal which is spatially encoded, resulting in images of the body. The uses of MRI are to find problems such as tumors, bleeding, injury, blood, vessel, diseases, or infection. To provide more information about a problem seen on an X-ray, ultrasound scan, or CT scan. An MRI can also scan the head area, chest, blood, blood vessels, abdomen, pelvis, bones, joints, and spines. The parts of an MRI are the radio frequency coil, the gradient coils, the magnets, the scanner, and the patient's table. And for it to work, a patient should be placed inside the scanner. MR imaging is based on the most prevalent atomic nucleus in the human body, the hydrogen atomic nucleus, which is found in tissue and blood. MRI uses powerful electromagnetic fields to affect the hydrogen atomic nuclei. The MRI machine generates a powerful static magnetic field. When exposed to this magnetic field, hydrogen atomic nuclei align themselves with the field generated by this magnet. A momentary burst of energy from a radio frequency coil positioned around the head excites the hydrogen nuclei. When this energy pulse is turned off, the nuclei return to their resting state and releases the energy that was stored during the pulse. It's that release of energy after the nuclei have been excited that is detected by the scanner and becomes the source of our data. Another magnet called a gradient coil makes the magnetic field to vary at different points in the brain. This allows us to determine whether the MRI signal is coming from. This week, radio frequency signals are then coded and decoded by a computer program. An image of the distribution of the hydrogen nuclei in the human body is generated.
Photoacoustic imaging is a biomedical imaging device that makes use of the photoacoustic effect. So what is this photoacoustic effect? The photoacoustic effect happens when sound waves are formed from light absorption. So we can actually deduce that from the term itself. Photo means light and acoustic is a word which refers to something related to sounds. So it can happen in two ways. So the first way is when it happens through a periodic pulsing of light. So when it happens through that form, it is also known as the modulated photoacoustic effect. And it can also happen in a second way, which is through a single flash of light. So when it happens through a single flash of light, it will be known as the pulsed photoacoustic effect. So basically, in photoacoustic imaging, we use non-ionizing laser pulses on biological tissues. The good thing about this is that it is a non-intrusive process, which means that we do not enter anything into the body. It all happens through waves. So from the energy given by the laser, it transforms into heat, and then the heat is what causes the transient thermoelastic expansion. So this thermoelastic expansion is the one which is responsible for forming the ultrasonic emission. And as we know, the human ear is incapable of hearing ultrasonic emissions. So in order to form the images, we use what we call ultrasonic transducers. That is what hears the ultrasonic emissions, which then transforms it into images. It is applied primarily in detecting changes in oxygenated or deoxygenated hemoglobin in small vessels. This is because the photoacoustic imaging can easily detect something which is related to hemoglobin concentration and oxygen saturation. But of course, photoacoustic imaging has great potential to improve in the future, especially with the innovative technology that we have today.
Tomography is from the Greek word tomos, which means slice, and graphia means describing. It is invented during 1972 by a British engineer, Godfrey Hounsfield, and of EMI Laboratories and Alan Cormack. It is the process of making an X-ray source move in one direction and an X-ray field moves in the opposite direction. The movement can be linear or the movement can be circular. A radiography is a 3D image of a body structure will be created. Using a computer, the output will be displayed and the cross-sections of the parts of the body along the axis will be shown. Using this kind of imaging, we can be able to see the tumors or the things that are inside the parts of our body.
So another type of biomedical imaging device is called medical ultrasound. Medical ultrasound falls into two distinct categories. One is diagnostic and the other one is therapeutic. Diagnostic ultrasound is a non-invasive diagnostic technique used to image inside the body. Ultrasound probes called transducers produce sound waves that have frequencies above the threshold of human hearing, which is above 20 kHz. But most transducers in the current use operate at much higher frequencies, which is in the megahertz range. Most diagnostic ultrasound probes are placed on the skin. However, to optimize image quality, probes may be placed inside the body by the gastrointestinal tract, vagina, blood vessels, or etc. In addition, ultrasound is sometimes used during surgery by placing a sterile probe into the area being operated on. Diagnostic ultrasound can be further subdivided into anatomical and functional ultrasound. Anatomical ultrasound produces image of internal organs or other structures, while functional ultrasound combines information such as the movement of the tissue or blood, softness or hardness of tissues, and other physical characteristics with anatomical images to create information maps. These maps help doctors visualize changes or differences in function within a structure or organ. The other category is the therapeutic ultrasound. Therapeutic ultrasound also uses sound waves above the range of human hearing, but does not produce images. Its purpose is to interact with tissues in the body, such that they are either modified or destroyed. Among the modifications possible are moving or pushing a tissue, heating tissue, dissolving blood clots, or delivering drugs to specific locations in the body. These destructive or ablative functions are made possible by use of very high-intensity beams that can destroy diseases or abnormal tissues, such as tumors. The advantage of using ultrasound therapies is that, in most cases, they are non-invasive. No incisions or cuts needed to be made to the skin, leaving no wounds or scars.